We're going to start the semester of General Anatomy and Physiology with Chapter 2, the chemical level of organization. And I'd like to start each lecture by looking at the learning outcomes, and this provides a nice outline, a nice preview of what we're going to be talking about in this chapter. So we're going to start with atoms, molecules and compounds. We're going to discuss chemical reactions and enzymes and how they're involved in chemical reactions. We'll then differentiate between organic and inorganic compounds and discuss the importance of water in chemistry. We're going to be looking at pH and how that plays a role in chemistry and functions of inorganic compounds, and then we look at the organic compounds like carbohydrates, lipids, proteins, nucleic acids, and a special type of nucleic acids, which is ATP. And then the last little section of this chapter ties it all together, how chemistry is important to cells. So you might be wondering, why are we starting anatomy and physiology with chemistry? Well, chemistry is a science that investigates matter and its interactions, and a basic understanding of chemistry helps us understand how the properties of atoms can affect cells and tissues, organs, and organ systems that make up the human body. And this is the reason for that prerequisite before you registered for a general A&P of 2 semesters of high school chemistry or 1 semester of college chemistry with a C or better. And so sometime this week, or maybe even at the beginning of next week, please, I just want to remind you, please complete the pre-GAP or the pre-GAP chemistry and math survey on Blackboard. Over the years, we've noticed a correlation between a strong chemistry background and strong understanding in general A&P. And so that's one of the reasons we kickstart the semester with this chapter. And so hopefully this is somewhat of a refresher for you. So we'll start at the beginning with matter. So matter is anything that takes up space and has mass. It's composed of elements like oxygen or sodium, and the smallest stable unit of matter is the atom. The atom. So atoms contain 3 major subatomic particles: protons, which have a mass and a positive electrical charge, and these are found in the atom's nucleus. Neutrons are another major subatomic particle. Neutrons have a mass and they are electrically neutral. They are not positive, they are not negative, they are neutral. Neutrons are also found in the atom's nucleus. And then last we have electrons. So this is the last subatomic particle. Electrons have very little mass and they have a negative electrical charge associated with them. They're typically found orbiting around the nucleus at high speeds in what we call an electron cloud or an electron shell. And pictured here is an example of an atom, if that can help you to kind of picture it in your mind. We have helium. So the element is helium, and it's represented by the abbreviation capital H, small e. And this is a 2-dimensional electron shell model, which makes it easy to visualize the atom's components. You can see the gray-colored neutrons and the kind of blue, dark blue protons that are forming the nucleus, and then the yellow-colored negatively charged electrons orbiting around the outside of that nucleus. So when we talk about atoms of an element, it's the number of protons that give an element its characteristics. Therefore, the number of protons never changes. So the number of protons never changes. Or if it did, it would be a different element. Okay? So the atomic number is the total of the number of protons and neutrons in the nucleus of an atom. It's not affected by gravity. It's an estimate of the atomic weight. The next vocabulary word that I have for you there is isotope. And isotopes is when you have an atom of an element with a different number of neutrons in the nucleus. And this is recognized by their mass number, because mass number is the total of protons and neutrons in the nucleus. And unstable isotopes are radioactive. They're used for diagnostic procedures. So the atomic weight, the last thing up there on this slide, the atomic weight is the average mass of an element's atoms. And it considers the influence of isotopes on the differences in mass. Now notice how the proton number always stayed the same. Okay? So that's what makes it an element. So in general, atoms are electrically neutral, meaning that the number of protons is typically balanced with the number of electrons. And we said that protons and neutrons are located, do you remember? It's in the nucleus. And electrons are orbiting the nucleus in shells. So it's the electrons in their outermost shell that can interact with other atoms then. So shells have this finite number of possible electrons that they can hold. An atom with an outer shell that is said to be filled is very stable or inert. And an atom with an outer shell that's not filled is going to be much more reactive with other atoms. So in a carbon atom, which has 6 protons and 6 electrons, the first shell is full, but the second shell contains only 4 electrons, and it wants 8. Okay? And so in a neon atom, the other one pictured here, in a neon atom which has 10 protons and 10 electrons, both the first shell and the second electron shell are filled. And so that neon is much less reactive. Okay? Whereas carbon can form 4 other bonds with other elements. So in my lectures, I have these checkpoints, and typically if you're looking at your textbook as you're listening to this lecture, you'll notice that these checkpoint questions or tasks are the same, and I usually pick just 1 or 2 and have, if this were an in-person lecture, I'd have you turn to the person next to you and talk about it. So if you can, just pause the lecture recording and see if you can do this. Can you define an atom? And pause the lecture recording and see if you can do that without looking back. See if you recall that information. Now the idea is that if you cannot recall that information, which we just defined an atom, so you're assessing your knowledge right now. If you can't remember it from memory, then you would go back and find it and then complete that task. So pause the lecture recording and see if you can define an atom. So the next section then looks at chemical bonds. Okay? And chemical bonds are anything that holds an atom together after a chemical reaction. And so this is going to be especially important for those unstable atoms that react with each other by either sharing or gaining or losing electrons. Okay? And so molecules then is what's formed, and molecules contain more than one atom that's bonded together by shared electrons. So can you think of an example of a molecule? An example of a molecule would be something like, hopefully you're coming up with like hydrogen gas, which is H2, or oxygen gas, which is O2, or nitrogen gas, which is N3. Now, one type of molecule is a compound. The compounds are made up of 2 or more elements bonded together by any one kind of chemical bond. So this would be something like carbon dioxide, or ammonia, or sodium chloride. So molecules are when you have atoms of the same elements, and compounds are different elements, 2 or more elements bonded together. Okay, so a little nuance there in the definition between molecules and compounds. Remember that I said most of the time atoms are electrically neutral, but some atoms will gain or lose electrons in the outer shell, and they'll do that to gain stability. And this is going to alter the atom's electric charge. So an atom that gains more electrons than it has protons will be negatively charged and is said to be an anion. An atom that loses more electrons than it has protons will then be positively charged because it's losing negatively charged particles, so it becomes more positive. And those more positively charged atoms are called cations. One of the tricks that I use to help myself remember anion versus cation, the T in cation looks like a plus in some different fonts. So that helps me remember positively charged cations. And cations and anions are electrically attracted to each other then, because anions are negatively charged, cations are positive, opposites attract. And ionic compounds are then formed by ionic bonds, this attraction between the cations and the anions. And so this is a figure from your book describing or depicting how those ionic bonds can be formed. So we have sodium, which has one electron in its outermost electron shell, which it's more than happy to give up. And chlorine, if you take a look at the chlorine atom below it, that one has 7 electrons in its outermost electron shell. So it's desperate for just one more electron to fill its outermost electron shell. And so when that happens, when sodium, that Na, when sodium gives away a negatively charged particle, it becomes more positive. And when chlorine accepts another electron and becomes more negative, those two atoms are now attracted to each other because one is positively charged and one is negatively charged. And like I said earlier, opposites attract, and that's how you form an ionic bond and the compound sodium chloride. Another type of bond, another way atoms can fill their outer electron shell is by sharing electrons with another atom. And the result is a molecule that's held together by covalent bonds. So a single covalent bond is when you share one pair of electrons, which is depicted right here with this hydrogen molecule here. That's a single covalent bond. Double covalent bonds is when you're sharing 2 pairs of electrons, like what's depicted here between the oxygens forming oxygen gas, or O2. And then they have an additional example of how you could have double bonds in carbon dioxide, the next compound below that. And so covalent bonds are relatively stable and strong because they are sharing these electrons rather than just giving them away or randomly accepting them. Covalent bonds are very strong. And there's 2 flavors of covalent bonds that you need to know about: polar and nonpolar covalent bonds. So these are, no matter what, these are covalent bonds. But the idea here is that in a nonpolar covalent bond, the electrons are equally shared between the different elements, the different atoms that are making up that molecule or compound. And this is probably what you were imagining anyways for most covalent bonds. And a lot of covalent bonds are just simply nonpolar covalent bonds. So this is just a regular covalent bond. The only reason that we specify nonpolar covalent bonds is because polar covalent bonds exist. And so in a polar covalent bond, you have these atoms that are more greedy, if you will, with the electrons. There's one element will share or hold more of the electrons more strongly than the other one. So if you think about it this way, oxygen is a much, much larger atom than hydrogen is, which is pictured here. So hydrogen has 1 proton and 1 electron, okay? And then oxygen has lots and lots of protons, lots and lots of positively charged particles, right? And so it's going to have lots and lots of electrons or negatively charged particles to balance out all of those positive protons. And so oxygen has this huge number of electrons compared to no electrons that the hydrogen has. The hydrogen is sharing its one and only electron with this gigantic oxygen molecule. And so what you end up with are these two protons, essentially, the nucleus of the hydrogen just kind of hanging out in space all by itself. And so that positive proton, which is all that's left of that hydrogen atom, forms this positive pole. And then this huge oxygen with all of its electrons forms what we call a negative pole, like a north and a south pole. So you have a negative pole and a positive pole. Okay, and so there's this unequal sharing of electrons. Oxygen has more electrons just because it's so much bigger, and so it creates this negative space. And then you have hydrogen, which creates these little positive ends that are just kind of hanging out in space. Okay, so that's why we call it a polar covalent bond, because it forms this negative and positive pole. Okay, and so these polar covalent bonds form polar molecules, which have this slightly negative end and a slightly positive end. And the reason that we talk about this with such emphasis is that these polar bonds can lead to hydrogen bonding, which is pictured here. So in addition to ionic and covalent bonds, you have these weaker attractive forces that can act between adjacent molecules and between atoms within large molecules. Okay, so now we're not just talking about two atoms acting together. Now we're talking about molecules acting together. Okay, and the most important of these weak attractive forces is the hydrogen bond, which is being pictured here. So these hydrogen bonds are too weak to create molecules, but they can alter the molecule's shape or pull molecules together, which is what you're seeing happening here in this H2O, this water. Okay, so water has this cohesive nature to it because of these hydrogen bonding between water molecules because of their polar covalent bonds. Okay, so what's happening is that slight positive charge on the hydrogen atom of a polar covalent bond and the slight negative of the next molecule, they're attracted to each other and they form these hydrogen bonds. And so we've reached another checkpoint in your textbook where I would like you to see, can you define a chemical bond and can you identify several types of chemical bonds? So this is the end of the first recording for Chapter 2, and we'll pick up with Section 2.3 in the next recording.